Fellow mathematicians, we're going to take a look at another simple area between curves question. However, this one requires a little bit more work. And the reason for that is here, we're just given a region bounded by two curves. We have no information about the interval of x values that we'd want to integrate over. Now let's start by just sketching each of those. From your knowledge of algebra, we have our basic parabola, which opens upwards. This one here, due to the negative in front of x squared, that's going to be a parabola that opens down. Now, you can easily sketch that by the intercepts. So if I rewrite that as 8x minus x squared, I'm going to factor x out. And you can see here your values of x for which y becomes 0. We would say the intercepts are going to be 0 and x equals 8. We know it's going to open downwards due to the negative, and it's going to pass through those 2 points. So let's do a quick sketch of our region. All right, we have our basic parabola, y equals x squared. And then our other parabola, again, it opens down and passes through those points, so passes through x equals 0. And this other intercept over here, that's 8. All right, and that is the graph of 8x minus x squared. Now, for a question like this, a region bounded by only two curves, those two curves have to enclose a single region. And if you notice here, basically between these points of intersection, we have a region enclosed by both of those curves. And we can set this up. We have a curve on the top, an upper function, and notice that function, that curve, the upper function is going to be 8x minus x squared, and then on the bottom is x squared. All right, so we can determine our upper and lower function easily from our sketch, but what we need to know is what that x value is. In other words, we're going to integrate from 0, but to what other x value? And the way we do that, we find the points of intersection is we take those two curves, set them equal to one another, and then solve that for x. So if we do that here, we're going to take y equals x squared, set that equal to y equals 8x minus x squared, where the two function values, or y values, are equal. That's where the graphs intersect, and we get a very simple quadratic equation. So we get x squared equals 8x minus x squared, and we can easily solve that. Let me go ahead and then let's put the x squareds on the left side so we have a positive in front. So I'll write that as 2x squared. I'm going to go ahead and then subtract 8x. And you can factor, it looks like 2x out from that. And then from here, if you set each of those to 0, you get two simple equations giving you x equals 0, which we already see from the graph here. And then the other intersection point, this one at the top there, that comes out to x equals 4. All right, and that's pretty much the work for setting up the integral to find the area of that region. We just have to set it up. We define it as an integral from here, 0 to 4, from your one intersection point here to the other intersection point, 4. And again, we can use our basic formula here, the upper function, but notice the upper function on top is 8x minus x squared. And then your function on the bottom right there, that's y equals x squared. All right, so if we set this up, it's going to be the upper 8x minus x squared, and then minus just x squared. You can use parentheses here, but since you're subtracting just x squared, that's not going to really make a difference. So we'll write that as minus x squared. And from there, it's just combining like terms. Notice we can rewrite this as the integral from 0 to 4, but now 8x minus 2 x squared. The function that you're integrating here, you can factor it completely by factoring it looks like 2x out, but remember, you can only pull constant multiples in front of the integral. So let's, from this function, factor out the common factor in terms of numbers, which is just 2. So this will make some of the calculations a little bit later a little bit easier. All right, so we'll write that now. We're factoring out 2 as the integral from 0 to 4 of now 4x, but minus x squared. And again, we factored out that common factor of 2 just to make some of the plugging in once we find an antiderivative a little bit easier. All right, here, very easy to find antiderivatives for each term. We're just going to apply the power rule. We'll keep that factor of 2 out front. And if we integrate term by term, 4x, that should integrate, we're getting a factor of a half, so that should integrate to 2x squared. And if you integrate x squared, that should come out to 1/3 x cubed. And we just need to evaluate that from x equals 0 to x equals 4. This one's also nice, like the previous problem. When you plug in x equals 0 to this antiderivative, the whole thing just evaluates to 0. And we just need to really plug in 4 to this. And if you go ahead and do that, so plug in 4, geez, basic math here, that's going to be what, 16 times 2, so 32. And if you plug in 4 there, that's going to give you what, 64 over 3. And you can work that out with a common denominator, multiply that by 2, and what you should get in the end is 64/3. And again, that is the area of the region here, bounded or enclosed by those 2 curves there. Again, this one was a little bit more work since we had to first find the points of intersection to set up the integral, but that's usually not too difficult. Usually comes down to some basic quadratic equations, which you can solve usually by factoring. Hope you enjoyed the video. I hope this is helping with your Calc 2 course. If it is, like and subscribe.